Good morning. And in today's class, we are going to learn about logic microoperations. Okay, so the microoperations most oftenly used in digital computers are classified into four categories: register transfer microoperations, arithmetic microoperations, logic microoperations, and shift microoperations. And we have learned already about register transfer microoperations. And in yesterday's class, we discussed about arithmetic microoperations, right? The main operations that are implemented are, addition, subtraction, and then increment and decrement. Okay, all this, the hardware circuit, if you see, it is implemented using a set of full adders. Okay, and here we are going to discuss this logic microoperations. The basic logic microoperations generally done in most of the computers are OR operation and complement operation and XOR. Okay, exclusive OR. These are the major, basic logic operations. OR and complement and XOR. Let's see these operations in detail. So first is OR microoperation. Okay, so here these operations focus on or perform these logic operations on bits. Okay, and here if you take this first OR operation, microoperation, the symbol used to represent this OR is, okay, OR microoperation is this. Okay, this is a symbol used to represent OR microoperation. And you should not confuse it with this plus. Okay, generally in microoperation, plus represents addition. Okay, we will not use plus in microoperations. Okay, when we write microoperations, we will never use plus to represent OR. We use only this symbol to represent the OR operation. And in Boolean functions or in control functions, okay, here if you see this statement, okay, which is given here, P plus Q, what is this? This is a control statement that is to be performed. This is not the micro operation, this is the control function. So here this plus represents OR. Okay, so we use plus to represent OR operation only in control functions, not in micro operation. And here if you see, this is the micro operation. Okay, R2, add the content of R2 and R3. Okay, so this plus represents add. Okay, this is add, and here R5, this operator is OR here, because this is a micro operation that performs the logic function OR on R5 and R6 and store the result in register R4. Okay, so here this denotes the OR operation. And here this plus in micro operation, this plus means add the content of R2 and R3 and store the result in R1. Okay, so here this plus represents add operation. And these are the micro operations. And here if you see P plus Q, this is the control function that controls these operations, okay, that are given here as R1, as R1, R2 plus R3, and R4 is R5 or R6. Okay, these functions, these micro operations are controlled by the control function P plus Q. Okay, so here this plus represents OR again, perform OR on the variables, okay, Boolean variables or control variables you call these, okay, P and Q, okay, perform OR operation on P and Q. And depending on the result, okay, based on the result you get after this OR operation, if it is 1, perform this logic operation, okay, micro operation. If it is 0, this operations, okay, will not be done. Okay, so not to get confused with the symbols used, I have given this statement, okay, this operations here. The OR operation, micro operation is represented using this symbol, and plus is used to add, okay, to represent addition only. In control functions, when we use plus, it denotes OR operation. And the gate used, okay, the logic gate used to perform this OR operation is this. So when you give the logic inputs, it performs OR and give us the output. Let's recollect this, the OR operation. Let's say X and Y are the inputs and Z is the output. 0, the inputs, 0 and 0 generate 0, okay, OR operation. 0 and 1 generates 1, 1 and 0 generates 1 again, 1 and 1 generates 1, okay. So when both the bits are 0, it is 0. When one of the bit is 1, it is 1. Okay, one example is given. You can perform this. 1 0 0 1 1 0 or, okay, the operator used is or here. It has 1 2 3 4 5 7 bits. 1 0 1 0 1 1 0. When you perform R, 0 1 or 1 is 1, here 1 0 1 1 1, okay. And the next operation is AND. The symbol used is this, okay. This is a symbol used to perform AND. And the gate, the logic gate used is this, okay. When the inputs are given, it performs AND operation. The truth table use, if you see X, Y, this is AND operation, X, Y, and Z. 0 and 0 generates 0, 0, 1 generates 0 again, 1 and 0 generates 0, only the 2 bits, okay. If the 2 bits are 1, the result would be 1, otherwise it is all zeros, okay. This is logic AND function, okay. So the result of this operation, okay, as given as example, 1 0 0 1 1 0 and 6 bits, 1 0 1 0 1 1. If you perform AND here, 1 and 0 becomes 0, 1 and 1 is 1, 1 0 is 0, 1 0 0 0, 1 1 is 1, okay. So the result is 1 3 zeros 1 0. This is AND, okay. You need to remember the symbols used, okay. For AND micro operation, the symbol used is this. The next operation we saw here in logic operation is complement. The symbol used is this, okay. The bar above the number, okay. The bar above the bits represent the complement operation. The gate used is this, and okay, if you see the truth table, let's say X is the input and Z is the output. It just complement the bits, okay. Whatever is the input given, if the input is 0, the result is 1. If the input is 1, the result will be 0, okay. It just complement the bits given as input. So here if you take this example, the number given is 1 0 1 0 1 1 0, okay. When you perform complement, okay, you get invert the bits 0 1 0 1 0 0 1. This is NOT operation. And the next operation is exclusive OR operation. The symbol used is this, okay. Plus symbol surrounding the circle, okay, surrounded with a circle, okay. This is the symbol used to represent this exclusive OR operation, okay. If the two content of two registers need to be XORed, okay, we say A XOR B, okay. This is how we represent this operation, micro operation. And the gate, okay, logic gate used as this. And the truth table, if we write X, Y are the input and Z is the output. 0 and 0 produces 0. Exclusive OR generates 0 if the bits are same, if the inputs are same, X and Y are same. If they are different, it produces 1, okay. So 0 1 produces 1, 1 0 generates 1, and 1 1 is 0. Okay, as the bits are same here, 1 1, it generates 0. Okay, this is XOR function. Okay, so if we take this example, the numbers given are 1 0 0 1 1 0, and the second number is 7-digit number 1 0 1 0 1 1 0. Perform XOR, same bits, result is 0. Here 1 and 1 0 0 0. Here 1 and 0 generates 1, 1 0 again generates 1, and here 1. Okay, so this is the result of this XOR. Okay, the symbol used is plus with a circle around. So these are all the basic logic operations: OR operation, AND microoperation, complement operation, okay, and then exclusive OR operation, and all the other operations. Okay, if suppose the operation need to be performed as A and B complement. Okay, this can be done by this basic operation, complement. Okay, already we have this complement operation. Okay, so if it is A and B, this is performed by AND operation. Okay, this is the AND micro operation, and when you complement, when you need to complement, this gate is used to complement the result of the AND. Okay, so it can be all the other operations can be implemented using these basic operations. So now hardware implementation, how these logic operations are implemented, okay, in digital computers. So there are, if you see, there are 16 different logic operations that can be performed with two binary variables. Okay, if you take two binary variables, X and Y, there are 16 different combinations. So we say that, okay, there are 16 different logic operations that can be performed. Let's so let's take this X and Y, okay, and the combinations X and Y are 0 0, and it can be 0 and 1, 1 0, and 1 1. Okay, so when the value of X and Y are, when these combinations 0 0 0 1 1 0 and 1 1, okay, this is our the two binary variables X and Y with these values. Okay, so what is X here? 0 0 1 1, and Y is 0 1 0 1. And the 16 different logical operations that can be performed can be represented using this functional, okay, this truth table. Let's say F naught, okay, is the first operation, and F1, F2, F3, F14, and F15. These are the 16, okay, functions that can be generated. F0 to 15, okay, totally 16. So here, if I write all the 16 combinations that can be made with all these two bits, okay, if I write it this way, 0 0 0 0, all the bits 0, and 0 0 0 1, okay, the least significant bit is, the last bit is 1 here, and 0 0 1 0 0 0 1 1 0 1 0 0 0 1 0 1 0 1 1 0 0 1 1 1, and here 1, all zeros, the next combination, correct? After 3 ones, we change this to 1. So 1 0 0 0. The next is 1 0 0 1, 1 0 1 0, 1 0 1 1, 1 1 0 0, 1 1 0 1, 1 1 1 0, all ones. So here if you see this table, F0, F1 up to F15, okay, 0 to 15 functions are generated here. Okay, if you see this, each of these columns, okay, each of the 16 columns, F0, okay, one column, and F1, the next function, okay, second column. So each column represents a truth table of one Boolean function, okay, one logic function. So here, the 16 logic. So here, as we have 16 columns, okay, there are 16 logic functions that is represented using this truth table. Okay, let's find what all those logic functions. Let me write the Boolean function. And the logic microoperation using the symbols. Then let's say what that particular operation mean. So here, if you take the first column F0, all the bits are 0. Okay, that means what is the meaning of this? Setting the value of the bit, okay, 0. So the function is F0 is assigning the value of this function, okay, F0 is 0. This is our micro operation performed. We use this transfer operation. Okay, we transfer 0 bits. Okay, when we want to clear a particular register. Okay, so we want to clear the set the value as 0. Okay, we use the function. We use the micro operation. This is clear. The name of this micro operation is clear. This is the first one, and the second operation. Okay, second column. If you see F1. So if you take this one, F1, the values are 0, 0, 0, 1. Okay, what is this micro operation? All the bits are 0. Okay, you see X and Y. Yes, check with this, and the result given is 0, 0, 0, 1. Okay, when there are two ones in X and Y, X and 1, X is 1 and Y is 1, the result is 1. And all the other cases it is 0. So the logic operation performed would be, so here the logic operation is Boolean function. Let's write the Boolean function. It is F1. Okay, F1 is equal to X, Y, means X and Y. 0, 0 produces 0, 0, 1, 1, 1, 0, 1, and 1, 1 is 1. This is R. Okay, but when the result is 0, 0, 1 is 0, 1, 0 is 0, 1, 1 is 1. So the result we got is this one, 0, 0, 0, 1. So this is AND operation. Okay, that's why here micro operation is micro operation XY for AND. It's not R. And here A and B. Okay, we use this symbol to represent and the operation performed is AND. And the third case. Third is column F2. Okay, so F2 is, what is the operation performed in this? Here 1, 0 is 1. All the other cases it is 0. Okay, so the operation performed here is X, Y complement. Okay, so if we have to check it, what is X? X is 0, 0, 1, 1. And Y complement. Y complement is 1. Y is 0, 1, 0, 1. So Y complement is Y, 1, 0, 1, 0. Okay, when you perform AND operation, you get 0, 0. Here 1 and 1 generates 1 and 1, 0 is 0. Okay, this is our result. Okay, this is X and this is Y complement. Okay, so the logic operation, micro operation performed is F is A and B complement. Okay, so the operation, name of the operation is AND only. Okay, we have written this, the same operation. And the fourth case, If you have any doubts in the middle, if you're not understanding any part, you can tell me. Then the next one, next function, let's take this F3. Okay, so what is F3? It is 0, 0, 1, 1. Okay, can anybody tell me what this is? Here it is x. F3 is equal to x. It is the same value. Okay, x is 0, 0, 1, 1. Okay, so the micro operation performed, you can say F is A. What is this operation? Okay, F, and writing this register transfer and TA. That means transfer the content of register A to F. And the fifth operation, F4, correct? And here the result is 0, 1, 0, 0. Okay, the second bit position 0 and 1, where there is 0 and 1 in x and y, we get 1 here. Okay, so this operation is F4 is x dash y, means x complement y. Okay, so here if we complement x, we get x complement is 1, 1, 0, 0, and y is 0, 1, 0, 1. Okay, when you perform AND operation, when you perform AND, the result is 0, 1, 0, 0. Okay, this is our F4. Okay, so here the operation performed is the micro operation involved in this function is x complement and y. Okay, so we write it here as A complement and B. Okay, this is already the operation, name of the operation is AND, we have already written. And the sixth one. Now let's take this F5. Okay, what is F5? F5 is 0, 1, 0, 1. Okay, it is, what is it? Okay, when we check with values of x and y, x is 0, 0, 1, 1, y is 0, 1, 0, 1. So this F5 is y. Okay, so the operation is F is equal to y. Okay, this is here we are using A and B, so let me write it as B. So the operation performed is transfer the content of B to F. And the next operation, F6, 0, 1, 1, 0. Okay, yeah, tell me what is the operation performed here. Yes. Check this function, the result is 0, 1, 1, 0. The input x and y are, okay, this. What is the operation performed here?
XOR, madam.
Correct, XOR. Okay, so here the operation performed F6. F6 is X exclusive or Y. Okay. And we write it here as F is A exclusive or B. Okay, the operation performed is XOR. And the next one, F7. If we take F7, the operation performed is, here the result is 0, 1, 1, 1. Okay, it is 0 only when there are zeros. Okay, so this is all the other cases 1. Okay, the result is 0 only when the inputs are 0. Okay, both the bits are 0. So the operation performed is R. X, P in logical, okay, in Boolean function plus represents R. So we write it this way, and here it is f is a or, it's not plus here, it is a or b. Okay, the or operation, the symbol is this. So the operation performed is or. And let's take the next operation, ninth one, f8. f8 is, what is the function here? 1 0 0 0. Okay, you see the previous case 0 1 1 1, and it is just the complement of this result f7. Okay, so can we say this as complement of previous one? Previous one is XOR y, and here XOR y complement. Okay, so the function is A or B complement. And what is the gate, logic gate, okay, that performs this function, complement of R? It is NOR. Okay, the function is, the name of the function is NOR. And the next operation, let's take this now, f9. f9 is 1 0 0 1. So it is, if you see this one here, this is exclusive OR. Okay, f6. Okay, f6, we said that it is exclusive OR, and this is the negation of that, correct? Complement of this result. So this must be x exclusive OR y complement. Okay, here we write this way, complement. Okay, we don't put the bar above, and here we use this symbol for complement. So the operation here is A exclusive OR B complement. Okay, so what is this operation? The complement of XOR. The negative operation, okay, of XOR is X NOR, right? Exclusive NOR operation that performs the complement of XOR. And the 11th operation, that is F10. F10 is 1 0 1 0. We had somewhere 0 1 0 1, right? Yeah, 0 1 0 1 is Y. And here it is 1 0 1 0, so it is Y complement. Okay, so the function is Y complement. Okay, so it's not Y here, B complement. And it is, the name of the function is complement B. Okay, and the next operation performed is F11 is 0 1 1 1. Okay, we have F11. So it is X or Y complement. Okay, so here if you take this, X is 0 0 1 1 and Y is 0 1 0 1, and if we take the complement 1 0 1 0, when we perform OR on this, okay, we get 1 0 1 1. Okay, so this operation is X or Y complement. And here when you write the micro operation, when you write A or B complement. Okay, so already we wrote it, OR operation is done. And the next 13, it is F12. If you take this, the operation performed is 1 1 0 0. Okay, it is, what is X? X is 0 0 1 1, it is the negation of that. Okay, so we can simply say that F12 is X complement. Okay, so the here it is A complement. And the function used is, means the name of the function is complement A, register A. And 14, the next operation is F13. F13 is 1101. It is X complement or Y. Okay, when you complement the bits of X and perform OR, okay, operation with Y, you get 1100. Okay, it is yes, X complement is 1100 and Y is 0101. So when we perform OR, it is 1101. Okay, so this is this F13. Okay, so the operation is X complement or Y. The function microoperation is A complement or B. Okay, this is another OR operation. And the next one, 15th operation is F14. This is F13. F14 is 1110. Correct. All the, it is when there are two ones, we have 0. Okay, it is AND operation generates 1 when there are two ones. But here, when there are two ones, it is 0. All the other cases, it is 1. So it is the negation of AND. Okay, we write it as XY complement. And the microoperation is A and B is complement. A and B complement. A and B complement. And what is the negation of AND? The operation is NAND. Negation AND. And the next operation, 16th one, if you see the last one, it is F15, all ones. Okay, that is, here we assigned a 0, first operation, F0. Okay, we assigned all zeros. So it is clearing the register, okay, setting the values to 0. And here assigning all to 1, setting the register values to 1. So it is 1, setting it to 1. Okay, so F15 is 1. The operation is set all values to 1. So here all these 16 operations, these are the, here we have and here. Okay, so all these 16 operations can be performed on these two variables. Okay, two binary variables X and Y. And this truth table show all the 16 operations. Each column represents one operation, one logic microoperation. Okay, that we have written here. And you have understood the symbols, right? The symbols used you need to be clear with. And the way how we write the Boolean functions and the corresponding microoperations we have written here. And for the implementation of hardware implementation of these microoperations now, okay, this hardware implementation requires that logic gates to be inserted for each bit or pair of bits in the registers to perform this logic function. Okay, to implement this, we need logic gates to be inserted because we need to perform this logic functions generally performed are AND or XOR and NOT, and where others can be derived, right? In this case, if you see A, yes, A and B, it's the basic operation. Okay, so here, and then XOR B. Okay, and we have complement. Okay, A complement or B complement. This is one operation, basic operation. And what all the other basic operations? R, where is R? Yeah, here, A or B. Okay, so all the other operations uses one of these operations. Here, the third one, okay, it is A and B. Okay, we have already A and B, and we also have a negation operator. Okay, so combination of this performs this operation. Okay, so the fundamental operations, okay, need to be focused. So here, this is the circuit that is used to implement these logic operations. Here, logic gates are inserted. Okay, the first gate is exclusive OR, and the second gate is OR. This is and not. Correct? XOR gate, we have OR gate, the four basic operations: XOR, OR, and not. Okay, to perform these four basic operations. Okay, this is the hardware circuit. Here, if you see AI and BI, okay, we are taking the ith bit, 2 bits. Okay, ith bit of A register and the ith bit of B register. And okay, these 2 bits are applied to these gates, XOR and then to OR gate, and these 2 bits are applied to AND gate also. And then this NOT operation, it takes a single bit, right? The input to a NOT gate is a single bit. Okay, so here AI is given as the input to NOT gate. And here we have a multiplexer. Okay, when we use a multiplexer, when we need one output, okay, from many inputs, we have many inputs, okay, and we need to select one input to be directed to the output. Okay, that case we select multiplexer, and we have 4 operations and one of the operation to be performed finally. Okay, what is required need to be performed. So to implement all these 4 operations using a single circuit, okay, finally we need one operation to be performed out of all these 4 operations. Okay, to select one among these 4 operations, we use multiplexer. Okay, this multiplexer, if you see, it is a 4x1 multiplexer. Okay, because it takes 4 inputs: input 0, input 1, input 2, and input 3. It takes 4 inputs and it gives us EI, one single output. Okay, one of this, the input 0 or input 1 or input 2 or input 3. Okay, one of this will be directed to the output. And how this, okay, so how it is controlled, the selection of input. For that we have selection lines S0 and S1. S1 and S0. Okay, the values can be 0 and 0, 0, 1, 1, 0, or 1, 1. Correct? So which particular input gets selected when the value of S0 is 0 and S1 is 0? Yes, I am waiting for your response. Multiplexer is a circuit that selects one input among many inputs, okay, and direct it as output. And that is controlled by which particular input to be selected is controlled by the selection lines S1 and S0. Okay, we have discussed in many earlier classes. So here, based on these inputs of S1 and S0, the multiplexer input, okay, one of the input gets selected. So when it is 0, 0, the input gets selected as?
XOR gate, ma'am. That is 0.
Correct. Okay, the input gets selected as 0. So that is the operation performed as XOR. Okay. So here, based on this circuit, the operation performed would be the output is AI is the first bit, okay. AI exclusive or BI. Okay, this is the output, and the operation performed is XOR. And the next case, okay, when it is 0 and 1, the output is, the input gets selected. So first case is XOR, okay, this gate, when it is 0 and 0, S1 and S0 are 0, this output, this input will get directed as output, okay. So what we get is XOR, okay, whatever the value of AI and BI, the corresponding output we get here, okay, from the multiplexer. And the second case, okay, S0 and S1, S0 and 1, okay. This case, when it is 0 and 1, the input gets selected as 1, okay. So this 1 will be directed to EI and output, and the operation performed is OR here, okay. We have OR gate. So the operation performed is AI or BI, okay. Operation is OR. And the third case, when S1 is 1 and S0 is 0, okay. When the values become 1 and 0, the input gets selected as 2, okay. This will be directed as output. And what is this 2? Is the output from AND gate. So the AND operation is performed, okay. In this case, AI and BI, the operation that is performed is AND. And the other case, the control inputs, both the inputs can be 1, okay. When both are 1, it select the third input of the multiplexer. So this get directed to as output. And what is this? The output of NOT gate, okay. Here we have a NOT gate. The output of NOT gate is coming as, applied as an input to the multiplexer, third input to the multiplexer. So here what is NOT? It is the negation of AI, okay. AI is connected to NOT, okay. So here we get AI complement, the complement of AI. This is our output, okay. This is, the result is EI. EI is equal to complement of AI. The operation performed here is complement. Okay, this way, this whole circuit is for one bit, okay, bit I, AI and BI, and you get the output EI. Okay, this need to be repeated, okay, this need to be constructed for, okay, many bits. That depends on the number of bits. Okay, so this way basic logic operations OR and XOR and NOT can be implemented. Okay, so we have here, we have seen about logic microoperations. The basic microoperations are OR and complement and XOR. Other operations, okay, like A and B complement, or A complement, B complement, or XOR, no, A XOR B complement, all these can be derived from these basic operations. Okay, and the hardware implementation, there are 16 different operations that can be performed. Logical micro operations can be performed on two binary variables. Okay, the two variables X and Y, and this truth table shows the 16 different functions obtained. Okay, micro operations that can be performed. So here, this is the hardware implementation. Okay, we need these logic gates to be inserted at the input end of the multiplexer. Okay, the output of these logic gates are applied to the multiplexer, and one of these input is selected, okay, as an output. And so using this circuit, we can perform these logic operations, micro operations. Any doubts in this? You can clarify if you have any doubts.